My name is Claudio Canizares. I'm at this point the acting director of the Institute. So it's my pleasure an honor to welcome Professor Gross, who has very kindly agreed to give this lecture. He's a professor at the Electrical and Computer Engineering Department and the Institute of Government and Public Affairs at the University of Illinois, Urbana-Champaign. His research and teaching activities are in the areas of power system analysis, economics and operation, utility regulation policy, and industry restructuring. He's one of the best-known researchers and professionals in this area, so it's an honor to have him here. His undergrad degree is from McGill, as a matter of fact, in Canada, and his grad studies are from the University of in Berkeley, California. He has consulted on electricity issues for utilities, government organizations, and research institutes, North America, South America, across the world. He has made a broad range of contributions in many areas: in power system planning, operation, analysis, and control. And his current work in the smart grids issues, which he'll be talking about some of it, concentrates on both technical and regulatory aspects of the smart grid. The principal areas of involvement include design of MI architecture to ensure the cybersecurity, the deployment of AMR for demand response, the integration of demand-side response, renewable and storage resources in the power grid, and also economic aspects of the smart grid industry. So it's my pleasure to welcome Professor Gross to talk about a practical framework for the implementation of the vehicle-to-grid V2G concept.
Okay. So this is a title, and in terms of background, I imagine we have people here from different areas, not just electrical and computer engineering. I imagine we have people from other areas, including the environmental ones. So there's very big interest in terms of climate change impacts. There's big interest in terms of greening of North America. And so we give us a very good success story. The fact that when Toyota Prius came out in North America, they sold in a very short period of time over 500,000 vehicles. In California today, if you want a Prius of a certain color, you still have to wait several months. Not in other parts. But California, certain colors are desirable, and so it comes with a price. So just so that we have the right terminology, I want to make sure that when I talk today about electric vehicles, battery vehicles, essentially I'm talking all types of vehicles, equal opportunity guy. So we talk about plug-in electric vehicles. We also talk about battery vehicles. I don't care if we have hybrids included or not, but essentially part of the driving mechanism comes through electricity. So that's what I mean over here. There is something interfering here with this, and I don't know what it is because I didn't touch it, and this is part of the idea of trying to use as a network over here. Okay, so I gave some examples of that. In terms of the talk, I'd like to talk about the integration of battery vehicles. So I'll talk about the battery vehicles, how they constitute a load, the battery vehicles, how they can constitute a generation or a storage device, which is very, very important for everything I'm talking about. And I'm going to bring out, throughout the presentation, the important role of aggregation. I'll talk about the implementation of the framework that we developed. And then I'm going to leave you with some of the key challenges that we still have in terms of the V2G vehicle to grid, so that everybody's on the same track. But what happened here? We moved now. We can't get the full slide in. I was going to say we move the wall, but that's a little bit difficult. This is the first time that it doesn't take. And then I'll conclude. Please ask any questions that you have. We don't have to wait till the very end because it will make things clear to other people. So I start first with price, which is a very important signal. And in terms of the electricity grid, and here we are in an area which does have a market and participates in market, as a province of Ontario has its own market system, the IESO. So megawatt hour costs and megawatt hour prices are not equal over time. They vary with time, very time varying phenomenon. And it depends very much, the price, the cost of every megawatt hour in terms of when it's produced and when it's consumed, okay? And so when we talk about integrating the battery vehicles into the grid, we want to take advantage of this time-varying nature of the commodity because megawatt hour is a commodity so that they can buy electricity when the prices are low and they can sell services when the prices become high, okay? I propose you guys don't try to do it the other way around because it's very fast, you go out of business that way. And also to take advantage of any opportunities to provide additional services that the grid may need. So here is a load curve. I've taken this out from the New England ISO. It's for a summer day. It happens to have two peaks that you can see that we have over there. With the two peaks. The earlier peak and then the later peak is even higher than the earlier peak because everybody comes home, turns on the television sets and so forth. And so we have a peak in the evening. So over here you can see this time varying nature of load. Very clear that we have a very nice average for the whole day. The average value is only achieved at 2 points during the day and it's momentary for all intents and purposes. Now also, let's look at the prices that we have. So these are the prices. I do it with respect to the right-hand side scale, and I show it in green. So green can have two meanings in my slides. It can either mean money or green electricity type of stuff. But you can see that the prices pretty much tracks the load. So the prices will vary as the load varies because we have to have different sets of resources to meet those loads. And again, we can get also a nice average value for the prices that exist. In that case, those are going to be occurring in this case because we have two peaks 4 times possibly during the daily period. So right now, the way we use the battery vehicle, be it a hybrid electric vehicle or wherever, it's essentially a load to the system. And what we have in terms of the daily cycle is we're going to charge it during the night. So the charging cycle is represented by the pink or lavender color over here. And then we start out in the morning and we go and take the car out after it's charged. We're going to drive with it and we're going to park it, probably for the duration of the day. When we're done with our work, we take it home. We're going to drive it home. We're going to put it into the receptacle and it's going to charge overnight so I can repeat the cycle for the next day. Okay, so this is purely as a load in terms of the role it has. And so people immediately started asking the question, okay, so what happens if when we get to 6 o'clock at night and all the guys in Brampton, Ontario come home and they're going to plug in their car, is that going to blow one of the substations out? Is that going to mean that we're going to have problems serving the load? So, you know, trends in North America start in California. So the study was done by the Electric Power Research Institute for the California load. And this is the daily load curve in California when we don't have any battery vehicles. You know, we kind of missed a very important thing with electric cars. They're still not buying them in enough numbers to get worried about this. And so I always say that if Steve Jobs were still alive, those electric vehicles would have a tremendous rebirth because he would come out with the iCar and everybody would buy it. But we missed that opportunity. Okay, so they did the study to put in 4 million public pluggable hybrid electric vehicles, and they tried to see what is going to be the impact if those were used in California. So California is a large state in terms of population, has a big load, though they've learned very well how to conserve stuff. And basically the biggest impact is at night. And at night, in any of the power systems in North America, we have a big problem. We have not enough load to basically support all the generators that want to be online, so next day they can also serve load. So in places like Ontario, you'll have prices like minus $60 during the night. In other words, the loads are paying, the generators are paying the loads to get online so that they don't have to shut down their system. Okay, so in California it would help because it would solve this low load problem during the night when we just don't have enough load. So the answer came back not at the level of the distribution system transformers or the substations, the distribution level, but in terms of system-wide, it would not be a very big problem. So we would like to basically look at, I think this university has an unstable electrical system, okay? That I can't help you with. That I didn't come to help you with. But this I've never seen before. I'm going to be able to write a paper on this very soon. Okay, so this is a California load. I did this. Okay, I'd like to talk about how it would be, how to effectively utilize the load, what we call to level the load. We don't like to have too many kinks or too much variability in the loads because we have to do a lot of frequency adjustments. We always want to have in power system, way before the economists even started talking about supply-demand balance, we need to always have supply-demand balance in the load and the supply. So here we have a load as it exists in this New England system. And so I want to kind of focus on that region which I drew over there as a circle and look at it. And what I'd like to do is use the electric vehicles in a controlled way so that I can levelize that load. Much easier for the operator. He doesn't have to stay up at night and worry about what's going to happen, if he's going to have enough resources, because he can levelize the load. So it will be much more like the Maytag repairman. He can think about his trip to Paris for next year. So the controlled impacts of charging the BVs is to try to charge all those battery vehicles during those valley periods so that we can levelize the load, and then for most of the night period, we could have a flat load. So certainly, that would be a very nice way to do it, because otherwise, we have to worry about the frequency issues. If we have too much generation, not enough load, then typically the frequency goes above the 60 hertz that we get over here. Your computers don't like it. The clocks, this kind of clock starts running fast. So maybe the clock is not correct because you did not have enough generation at one point, and then it's slower and it slows down. So let me kind of show you, because of that, what we need in the power system, we need regulation service. And so here are signals that one of the operators sends out. The largest one in North America is PJM. And the operator sends out signals basically asking generators to either raise their load, so it's above zero, please produce a little bit more generation than you did before, or to lower the load. Okay, so cut back in terms of production because we have overgeneration. And what's very interesting is just as the signal varies with time, so does the price. So the prices here are a little bit different because we are delivering basically just standby service that we can reduce the load, so it's dollars per megawatt per hour. While previously I gave you dollars per megawatt hour. So I'm not selling the same service here. This is a regulation service where I'm trying to make sure that the supply and the demand are exactly in equilibrium. So you can see that much of the day on the, with the green scale, much of the day we have basically flat prices, but at night we have some very big prices because nobody wants to reduce their load. So we have very large prices during the day because we need big reductions of the load because there's too much generation online. I have to have those generators on even if they are at the minimum loading, because next day I will need them and they will have to produce more power. If I shut them down, it will take me many hours to start them up again because I have various thermal forces which I have to be in equilibrium, they have to come to rest and so forth. So that's why you can see the very high prices for the service, because people just don't want to reduce their load during the night, their loading during the night. Okay, so we have a nice average price, but that exists only at very few instances during the entire day in terms of the regulation price. So I want to look and explore the role that battery vehicles can play in terms of frequency regulation service provision. So this is what we call frequency regulation. It's done via a grid control mechanism, which is called AGC, automatic generation control, but very, very important because every North American utility uses that. It's not universal throughout the world. They don't have it in England, for example. They don't have it every country in South America, but in North America we use it. So I talked about supply-demand balance. And this is exactly what we have to do. We have to do it 24/7, but we have to do it second by second, okay? So it's a continuing type of mechanism that the power system operator must provide. Anytime we have certain imbalances in the system, that leads to frequency deviation. So here in North America, we have 60 hertz, 60 cycles per second. South America, most countries are 50 hertz over there. Basically, those frequencies either lag or lead, they become too high or they become too low. We're operating in North America within very strict limits over there. It's probably thousands of hertz in many places, some places hundreds of hertz cycle per second. So the supply-demand imbalance is checked automatically every 2 to 4 seconds. That will depend on the region that we're talking about in terms of when it's done. The idea is that here we have the daily load that we talked about, and I want to see exactly what happens in that region there which I'm focusing on. And you can see I'm plotting generation with one color, and then with lavender I'm plotting the load. Okay, and sometimes the generation is above the load, so I have too much generation. That means signals go out from the operator, please reduce your load in the next 2 to 4 seconds. Sometimes it's below the load, please increase your generation in the next 2 to 4 seconds. So the idea is that can we use this kind of structure to see if we could take advantage of battery vehicles. So you look at battery vehicles and then you look at the imbalances which may occur between the load and the supply. Supply is shown in blue in this curve, and the load is shown in green. Demand, load, we'll treat them as the same. So I'm stealing this pictorial representation from another publication, and the guy who was doing my slide was too lazy to recolor it, so I'm using different colors to kind of make sure that the audience is still up after me talking 20 minutes. Okay, and so you can see that we could use those battery vehicles to supply service when we have a certain kind of service. So when we have that the demand, we have the green is above the blue, Okay, we have too much demand, so what we have to do is basically raise the generation. So you discharge some of the batteries. In the other instance over there, when we have the supply is above the demand, we are going to basically charge those batteries because they're going to essentially increase the demand on the system. It's going to increase the load. So there's some symbiotic effect over there where these vehicles could come in and be of use. The fact that at night, what we call off-peak regulation is a very critical problem. That's what we want to take particular advantage of because at night we want to charge the vehicles because electricity is much cheaper. And so people go to sleep. They don't necessarily need their cars. I'm really looking in this entire presentation. I'm assuming the car is used primarily for commuting purposes. Okay, so that's the basis of the studies that I'm doing over here. So I have to comply with the unit commitment schedules. That means every day the operator decides which units will be supplying the demand the next day. So those are the schedules. But it can happen that because we have too little load and too much generation running online, we may have to shut off some units. Operator doesn't like to shut down units, but sometimes he has no choice because if he keeps them on, then we're going to have this stuff that we have too high a frequency in the system, cannot operate with that, so it has self-protection mechanism and it would just disconnect those generators. As we brought in more and more wind, that situation gets worse because particularly in the Ontario area, the Midwest where I happen to live, the wind likes to blow at night. Not during the day when we really need it because we could use that generation, it would be green generation, but it blows at night. So this situation with low load conditions is exacerbated by the fact that we have deepening penetration of wind. So the regulation prices at night happen to be some of the highest. And what I've done over here is look at the number of days with prices for regulation above $250 per megawatt per hour. This is in California. And I put this on a daily basis from midnight all the way to the next midnight. And you can see that some of the highest prices in the highest frequencies happen to be between the hours 0 and 8. Go ahead.
What is the up-regulation price?
California has different products. So when you raise the generation, it's called regulation up. When you lower the generation, is a regulation down.
But the up-regulation prices are lower than the down-regulation price?
Yeah. It's very easy to raise because there's a lot of generators there so they can raise the output. They don't mind doing it. But nobody wants to shut down. So because they don't want to shut down, they ask for higher prices to make it worth their while because they can't participate then in the markets the following day.
Oh, so these are not the prices, these are number of...
No, this is a number of days when we have prices higher than $250.
So these are histogram number of days.
Yeah, it's a number of days in a month. Okay? But that event occurs during those hours much more frequently in terms of having to lower the generation. So this is like a motivation why we're so interested in what happens at night. So let's just talk about battery vehicles and frequency regulation. We know that batteries are good because they can both absorb and they also can discharge energy. Okay, so there's both a source and a sink, not at the same time, either one or the other. If you do it at the same time, you don't do anything because you cancel each other. Then the regulation capacity provided by any single BV battery is going to be very small, not in any way palpable to the system. The system will see that as noise, okay? So batteries, however, have a very good response time. In other words, you tell them charge, they charge. You tell them discharge, they discharge. So there's no latency in the system. They respond very, very quickly once they get the signal. We also know that it doesn't do very much good for any single battery to be switched on and to be switched off and to be charged and discharged. So we have to do this in a very judicious way in terms of how we use them. So I want to look now at the complement of what we were looking before in terms of the daily cycle of using the battery vehicles, but I'd like to look at that as a supply side resource during the time that it's parked, say at the office, in a garage, and so forth, and the person is just working, and that car is basically idle. We could be using it for the purpose of doing some regulation services, or even better, of supplying backup. You know, every time you do operations, you always have to have a spare tire. The spare tire in power systems is called reserves. So we always dedicate a certain amount of capacity which is already energized and synchronized with the system, but we cannot devote it for any other purpose because we're holding it back just in case the regular tire goes, so then I have to make use of the spare tire. So that's the way I want to look at this. So we want to look first of all at capability. So I make a distinction here. I use the word capability when I talk about the amount of energy I store. Capacity is the rate at which I charge it or discharge it. So I distinguish between those two. That's why I'm using the word capability. But for any single battery that's small, particularly from a system point of view, because the system is at the bulk level, at the order of hundreds and hundreds of megawatts and thousands and thousands of megawatt hours. So because we have this limitation in terms of size, the supply side resource is of not very much usefulness just by itself for a single battery vehicle battery. So in order to be able to integrate these battery vehicles into the grid, what we have to do is we need to get an aggregation of them. They don't necessarily have to be co-located at the same location, but there has to be one entity which interfaces with the grid to present what an aggregation of these battery vehicles can do. So I'm bringing in that we need to have an aggregator who can make this aggregation to be something that's palpable to the system, so the system doesn't think that it only senses noise over there. So in terms of the aggregation, if I look at a single battery for a typical BV, it's in the range of 10 to 50 kilowatt hour range, so the capability, okay? And we typically say that we can charge him full or discharge him full. You never want to do either necessarily in terms of battery life, on the order of 5 hours. So in terms of, if we say that we have 10 to 50 kilowatt hour range for capability over 5 hours, that means that they can operate at 2 to 10 kilowatts for each of those batteries. So the aggregator goes, and this idea for the aggregator comes purely from demand side management, where we have, say, the large buildings in Toronto were gathered together by an aggregator and said that I'm going to put these guys as a single block, and the utility can deal with me if they want us to reduce the load by, say, 100 megawatts for 1 hour. We can do that. We'll make the elevators run a little bit slower. We might reduce the lighting for a few minutes. It's not necessarily means that we do it over the entire hour, because my aggregation is large. So I do it in the sense that everybody's out for a few seconds, and then the next group comes in, and the next group. So at any one time, only a small percentage of the total aggregation will have a lowering of their energy. But over the whole hour, I'll be able to cut 100 megawatts down, so I can save 100 megawatt hours of electricity during that hour. So same idea is done here for these electric vehicles to put together an aggregation so that it becomes palpable to the system operator, and they can offer the kind of services that that the system operator needs. So with aggregation and with looking at the battery vehicles, both from the load side and also from the supply side, the resource side, I'm going to talk about the framework. So I'll base my stuff on what I said so far on load aggregation. We'll talk a little bit more about resource aggregation. And then you're going to say, well, what about the guy who says he's there, but at 2 o'clock he's got a dentist appointment? So I want to bring in explicitly the representation of uncertainty that some guys may not be there, even though they're working for 8 hours, but they have appointments and it takes their car out. How does that impact? So I'm going to discuss that topic, and then I'll talk about what we do in terms of an information, communications, control layer, what are the basic requirements, and then how does an aggregator go about and build this aggregation? He has to have some carrots, not only sticks, but he has to have some carrots. What kind of commands is he going to tell the aggregators, come and join my aggregation because it's going to be better for you? So that's what I want to discuss. And so let's kind of lay out what are the principal roles that are being played in this framework. We have to have the aggregator, a new player who does not exist. It doesn't mean that the local distribution company couldn't be that player, but it's somebody who is going to have to discharge this function that today doesn't exist. We'll talk about the aggregated BVs. That's basically the Greek chorus that is being directed by the aggregator. We'll talk about the independent system operators, sometimes called in the US the regional transmission organization. Basically, the entity that operates the bulk power system. Then we have the energy services provider. That's a guy who interfaces directly with the customer, electrical customer. And then we have the local distribution company. In some places, ESP doesn't exist, so it could be the same thing as a local distribution company. In some places, we have an ESP who provides that service. So for the integration framework, I need the aggregator to play the role of taking all the battery vehicles and aggregating them as a single load when they buy electricity, which means that he could go out and buy in bulk electricity for those guys and try to resell it to the loads, but at a cheaper price. So I'm already painting the picture of the future where I believe that none of the regulators is going to allow the battery vehicles to be served electricity at the same price that you buy electricity to run your refrigerator, your washing machine, or your dryer, because it's going to be seen as a source of taxes. For example, if we have an electric vehicle, it's not going to buy gasoline. Somebody will still have to go and maintain those roads because your potholes in Ontario are fantastic. You guys could get first prize for the North American continent, as far as I'm concerned. Unbelievable. Chicago was competing with you. I think it's losing. Okay? The aggregator also has to come and provide a service for the resources when we want to run these guys to maybe provide this frequency regulation, so he's going to aggregate them. It doesn't mean that all these cars have to be in one parking lot, but he will have to be connected via some kind of communication networks that he can offer that service to the grid. So as an example, I would say a place like all the parking lots around the Pearson Airport is a good candidate to start with because you have enough space there to put together some sizable aggregations and bring them on. You know, I just learned this week, Norway has more Teslas per capita than even California does. Okay? Why? Because they passed a law which says that if you're importing an electric vehicle, then you don't have to pay duty on it. You have to do it on the BMWs, and you have to do it on the Audis, and you have to do it on the American cars, but not on Tesla, because it's an electric vehicle. So the taxes in Oslo happen to be Teslas. Okay, because it's cheaper to buy one of those cars than to pay the 300% duty on the other cars. So this is nice government policy to push along this agenda that we would like to have more of these green vehicles. So in terms of the interactions that we have, the network at the ISO RTO level in terms of the system operator, he interacts directly with the aggregator. So I want to be very fancy, and I use the Greek symbol sigma to talk for aggregator. That's because I ran out of English letters, so that's the only reason. That aggregator does liaison not only with individual BV owners or BV users, but he goes and lines up the facility for parking for these guys. He gets lower rates, and that's part of the incentives he can give. He also has to discuss issues with the battery suppliers, because he is using that as a way for him to sell services or to buy services. So he will have to know very much about battery technology and how to manage those batteries, because it's going to be in his interest to manage it as effectively and to lengthen the life of those batteries, and not to do any kind of activities which will shorten that life. And so we have then the two aggregations. The load on one side, we have the aggregation of the resources. And here I have two types of flows. I have flows of dollars, and I have also flows of physical flows in terms of electricity. So the solid line is the electricity flow. It can be in terms of capacity or energy. And then the broken lines are the dollar flows, so that we can differentiate between them. So all the flows here are brought out, but we're also adding the signals, because the system operator has to be able to send those signals: raise generation, lower generation, give me some energy, and so forth. So those are shown now in dotted lines.
So is it directly with the system operator or some local LDC?
No. This is at the level of today's operations, that the vehicles would be providing services to the power grid, not to the distribution company. When I come next time, I'll talk about microgrids, then I'll put on that hat, okay? But this is at the level of the system operator at the IESO level in Toronto, in terms of making sure that at the bulk level we do that. So the charging of the vehicle will be done at the distribution level. And so you also have to put in the fact that you're going to be talking to the distribution company, because you're going to use those wires to be able to charge them. So in terms of, I put the aggregator at the center, because he gets all the signals and he distributes them to the vehicles, whether they're parked at home. So at home, we can do the levelization of the load at the direction, say, of the local distribution company, because he wants to levelize load. But during the day, when they're parked at the offices, then it would be done to make sure that they can be used also for frequency regulation. So I want to talk a little bit about uncertainty, because that's always important, because there will be always exceptions to the rule. So what kind of uncertainty are we talking about? Well, people don't exactly behave the same way in North America. They get up when they want to get up. They arrive at the office when they want to come there. The number of hours they're going to park is going to change. And a key variable in terms of battery is the state of charge. So that's essentially the key metrics that we use to say, where is the battery? Can you provide energy? Do you need more energy because you're too discharged? And then we have to know about each car. I mean, we're going to have multiplicity of car manufacturers, so the storage capability may not be the same. Now, this won't happen if it's up to Elon Musk, who runs Tesla, because he wants to be in the battery business. So he's building this giant $5 billion battery factory, which he wants to use to be able to reduce the price of Tesla to $35,000, okay? He can be, he's very successful because he got $5 billion from Panasonic, and he got $1.25 billion from the Nevada government in terms of tax benefits and incentives. So he can do it because he's using other people's money. But if he's successful, I think that's going to get this thing going, because he's going to reduce the price of batteries, and then he's going to leave Tesla, and he's going to start competing against the utilities because he can do batteries very cheaply. So that's coming. The saga will continue. So now because we're talking about large aggregations of vehicles, we want to use results from statistics. So we'll use the central limit theorem. So the law of large numbers. Essentially, we're looking at independent, identically distributed random variables, and then we can, everything behaves like a Gaussian distribution. Okay, so we're going to use that because we're going to talk about large aggregations. Okay, so first of all, let me start by looking at daily commute distances. Okay, so when we look, this is basically cumulative percentages in terms of what is the distances. So you can look at this as a cumulative distribution function, and then I drop the 50% line, and I find that on average, all over North America, average commute distance is 22 miles, so about 35 kilometers. I had to change this slide because I know that in Canada now we work with kilometers and kilograms. So this was one of the ones, extra preparation for Waterloo. So it's 35 kilometers, so you can see that means that there are people. I remember when I worked at PG&E in San Francisco, there were guys who were coming in from Sacramento, 90 miles each direction. So they were commuting 180 miles to get to work. So the government really wanted to basically incentivize this kind of commute, so they gave them free trucks to take also other people to reduce the number of cars on the road. So you look at it. But it's 35 kilometers essentially is the average. So that means it's good in terms of looking at the car. At the car, you would probably have it parked, if you don't use it to run errands and so forth, on average 22 hours a day. Let's assume it's 1 hour to commute in one direction, 1 hour in the other direction. So let's look at this law of large numbers, and I'm looking here at a parking lot. This is data taken from Livermore, and day 1, you can see the pattern over there. Day 2 is slightly different. Day 3 is again slightly different. And let me pass an approximation with the normal distribution. So it really captures all the characteristics, okay? It captures all the characteristics. Of course, I'm going to have to basically abridge it somehow, just like Reader's Digest is abridged in some way, but cut it off because I'm not going to have negative values going in there. But it's a pretty good approximation when we do this normal stuff. So this is the basis that we did our work in terms of bringing in uncertainties, that we have so many independent vehicles. They don't have to have the same charge and so forth, but we can get a nice bell-shaped curve in terms of their distribution. So I didn't talk much about the state of charge of the battery, and so I should spend a little time. It's a very important metric, okay? It tells me basically what I can use that battery for. So we do a very simple classification over here. If the state of charge is below 60%, then we don't want to discharge that battery anymore. We would just like to charge it. So below 60%, the battery vehicle will act as a demand-side resource. If it is above 80%, then we can discharge it because we have a lot of charge over there, so it can be a supply-side resource. And then between 60 and 80, you can have it as either or, but please not both, because then they cancel each other. So it's either or. Okay, so the utilization of a battery is very much a function of how much I can store in that battery. Whether I can put 10 kilowatt hours or 50 kilowatt hours, I'm going to have different types of resources and impacts. So when I take all the aggregated battery vehicles, they can bring together essentially it's an aggregation, something that can impact the system. So they have the potential to constitute a very important supply side resource to the grid, not only demand, but also supply. So because of the fast response, they can help the regulator basically be very flexible, because now with all the time varying impacts of having renewable resources, we can have the problem with intermittency. Basically, we have a cloud going over the solar panel, and all of a sudden its output goes to zero. The load doesn't change in the rest of the system. The power system operator has to be able to cover that, so he's got fast responding devices. He can get that from the batteries, which are aggregator. But as a result of the fact that we can use these batteries, essentially backup type of stuff, I'm going to change the way I commit the units, because usually in terms of this is my system over here, and I'm looking at those two peaks. I'm going to use peaking units to meet the very, very high load of the day. I'm going to use some cycling units to meet the other loads just below it. They call cycling because they're up sometime and then they're down sometime, so they cycle between being all the way at their full power or at a lower output. So in order to be able to do that, I have to have both the peaking unit and the cycling unit started a number of hours before, because I have to start up those cycling units. The peaking units are very fast responding, meaning I can get some of the gas turbines to be online and full output in 5 minutes, but the cycling units takes longer. So I would start those cycling units sometimes at 6 o'clock in the morning to be able to provide output for the first peak and then also for the second peak. Now, if I bring in, on the other hand, I'm going to bring in the V2G, what I can do is use basically that peak to be served by the V2G, and I can start up those cycling units at a much later time. So that flexibility means that they operate fewer hours, they pollute fewer hours, so in effect we can get slightly cleaner energy. So that would be a very, very beneficial impact that we can get. So this is the additional flexibility that those battery vehicles can provide to the system operator. So by having that delay in terms of the startup, that means I pollute less during that entire period. So I wanted to give you some examples of simulations that we did. We wanted to look at the regulation service. This is the signal from PJM that we're using. And then this signal has to be translated into the signals that the system operator would use and send to an aggregation of vehicles. So I'm putting here together, for simulation purposes, don't ask me how did I convince 100,000 battery electric vehicles. We don't have that many. In terms of plug-in hybrids, in the last 4 years, we sold something like 130,000 of them in California. So the rush is not on yet to buy these vehicles. But essentially, this would be the raise lower signals that I would send to provide frequency regulation. On the positive side, we're asking those electric vehicles to produce more output. On the negative side, they're being used for charging. And from this 100,000 vehicles, so this is plus or minus 30 megawatts service provided. I'm looking here at the percentage of BVs that provide this 30 megawatts between 8 o'clock in the evening and 6 o'clock at night. So at no point do I have more than 8% of those vehicles involved. Okay, so I'm providing 30 megawatt of service, but with less than 8% of the vehicles at any one point in time. I do it Robin-Ness fashion, basically. This guy's for 6 minutes, this guy's for 6 minutes, and so forth. So I don't impact any of the vehicles over a long period of time. So I can do this service of 30 megawatts plus or minus with somewhere between 6 and 8%, but certainly less than 8% of the vehicles. So key message there that to provide this regulation service, I don't use all the vehicles all the time, but I just use a small percentage of it. So now we'll ratchet up the problem a little bit in terms of saying that not only provide me regulation service, but can you also give me load shaving service? Basically, provide some of the energy. So specifically, I want you to provide from those 100,000 vehicles, provide me 100 megawatt hours of load shaving service between the period of 9 a.m. and 9:30 a.m. Okay, so here is what happens in terms of the percentage of vehicles involved. All of a sudden, that quantity less than 8% jumps up to nearly 60% for that half an hour, when we're also basically discharging some of these vehicles. Still not 100%, still going to be just a fraction of the total vehicles. But only for that half an hour, and then it goes back exactly the same way as it was before. So this is simulation results. So that begets the question, okay, so how big an aggregation do I have to be able to provide this 100 megawatts of service together with the plus or minus 30 megawatts of regulation service? And so we ratcheted it down from 100,000 to about 60,000 and then to 50,000. But when we get to about 45,000, we cannot provide that amount of 100 megawatt hours for that half an hour. Okay? In fact, we could provide more for anything over 50,000. As you can see, it can go up all the way to 200 megawatt hours. But as we come down and the size of the aggregation decreases, there's a limit that we run in there. So this also tries to look at the same kind of question. So here we have the time of day and the regulation service that's demanded. So, and particularly, I'm looking in the night hours over here in terms of what's demanded. You can see primarily you want down regulation, meaning you want to basically lower the amount of generation.
How are you modeling the regulation service? In what?
So this is just the demand.
No, but what is the overall framework of your problem? Like, is it what kind of model are you using?
I'm just looking at the capability of so many thousand vehicles, what service they can provide, what is the maximum output they can provide for this period. So it's a period between midnight and 6 a.m. But this is purely the demand over here that you see. And I can show you, when I put in 10,000 vehicles, it doesn't even change it very much, except at the bottom a bit in terms of reducing it. When I put in 50,000 vehicles, a little bit more. When I put in 100,000, then it's starting to have a little bit of an impact.
Is that demand for regulation?
That's what the ISO sends out.
Also, it's a predetermined
Yeah.
value.
Well, I mean, I'm using a historical. Yeah, I'm using a historical data over here. So that's with 100,000 vehicles. Now, when I put in 500,000 vehicles, I could actually flatten the load. Okay, with 500,000 vehicles as an aggregation, then we can have some real impact in terms of all the services provided by 500,000 vehicles. So that's what it is. So let me get to some of the key implementation issues, because I don't want to keep you guys too long. The aggregation issue, how do you go out and form these aggregations? Then the construction of the information communication control layer and the development of incentives. And another one, because this is very important in terms of selling the idea, is the fact that this aggregator would be the only one who could provide reliable information on the realization of environmental benefits. As a single vehicle, a battery vehicle, yeah, does something, but nobody can monitor it at the level of the bulk power system. However, the aggregator can when he has 100,000 vehicles. He can monitor that and he can provide those results. So in terms of the communication and metering infrastructure that's needed, very important too, and it's very important that it be secure, because if it is connected to the grid, it's another portal that we have for through each of these battery vehicles to try to hack the grid. And not that it's something out of science fiction, something that happens. Go ahead.
Yes, do you consider the impact on the battery lifetime of this kind of regulation?
So yeah, we of course we have to do that, and that's another problem over there. But that's a problem independent of whether the vehicles are used for V2G or not, because one of the things I'm going to propose is that the aggregator can get into the business of being in the battery management business. He buys these batteries in bulk. He sells them to the individual customers. He's going to say, you don't own the battery, I own the battery, so I'm going to do the best because I want to make sure that I get as much life of those batteries as possible. So that's the mindset over here. But basically, we need communication to be able to talk to each of the vehicles. We need communications to talk to the system operator, and we need communications to talk to the, whether it's a distribution company or the electricity service provider. We need that. So that network most likely implemented today in a wireless sense, or perhaps on the basis of the internet. But it's not going to be fiber-based type of stuff, because first of all, the vehicles have to travel big distances, and I have to be able to communicate with each vehicle. So the first thing that we're thinking of is to put essentially something like a SIMS card on each of the vehicles, so that I can get the identity of the battery, not so much the vehicle, so that basically I can charge that battery the fees that are associated with the services I provide, or pay that battery if it provides services to the grid. So in terms of key requirements for the communications control system, we have to have speed. Signals need to be sent every 1 to 2 seconds. Can't have any kind of big latency in that kind of a system. The range, I have to be able to reach every battery vehicle which is in my aggregation, be it in the parking lot, be it at the residence. The measurement, it means that I have to have sensing and metering to be installed to enable payment for services or payment of services provided in either direction. And then I have to have very good reliability, because I want to make use of as many of the parked vehicles as possible. The security is a key issue because of cyber issues, and so the costs are another issue. Those battery vehicles are already expensive, so they're not exactly willing to pay yet another cost so that you can use them in a V2G type of stuff. So the add-on of the cost in terms of a communication system has to be very, very low, but essentially not of an impact whether somebody buys or doesn't buy a car. And then we have to have not only modularity but also extendability, because as we get more and more vehicles into the aggregation, we have to be able to integrate them into that network. Clearly, we will need to have interoperability if we want to have this part of the grid and so forth, so all of those requirements are met. But just very quickly, information layer flows. There's not that much information, and I'm only going to be interested in collecting information if there is a change from the previous value. If there isn't, I don't have to collect it, or I don't have to transmit that data. So I'm going to have that kind of checking in terms of making sure that I'm not wasting any kind of resources on that. The roles of the aggregator, I put down here all the roles I see the aggregator providing in terms of developing the parking infrastructure and the incentives associated for it. So he has to undercut, like the parking, your university probably makes more money from parking fees than they make from tuition, from what I can tell, because they basically charge rates that they would charge downtown Chicago, at least for visitors, so I don't know. I'm still a Canadian citizen, so they should have given me a good deal, but they didn't. So they have to do the battery maintenance, and they have to create relationship with all the manufacturers, because they're going to have new cars coming in, so they have to know the technology, be it of the car, be it of the battery. And then they interface with the system operator. And so I want to think of the aggregator as someone who provides a package deal, basically in terms of having everything together. You get the parking, you get the service acquisition and provision, you charge as the BVs, and you provide battery service to them. And he also has to act as a representative of all the battery vehicles when it comes to both the electricity suppliers and also to the system operator. So just a couple of slides in terms of looking at emissions of CO2 in terms of grams per kilowatt hour. Clearly wind, hydro, nuclear are basically very low emissions type of devices. Solar a little bit higher because of certain assumptions that we make, and then we have natural gas, and compared to that, both petroleum and coal are twice as bad in terms of emissions. So that's why there's this rush to gas, because it's relatively clean. In terms of energy consumption under mixed conditions, depending where that generation comes from. Okay, so and for different cars, so I have the number of kilowatt hours here per kilometers, and this has to be mixed conditions in terms of looking at the overall picture. So you can see that depending miles EV, typically the market that exists for miles is in California. So this is California conditions, and California operates as a state because they like to export pollution. So they rather pay higher prices, but they want that pollution to be in other states like Arizona or Wyoming, and just import the electricity. And for different cars, we can see some figures over there. In terms of CO2 emissions, it certainly depends on where the electricity is produced. So an electric vehicle in France has very low, because France happens to be 88% hydro and nuclear, and so they have not much thermal generation in comparison. Canada also has a lot of hydro, so electric vehicles are relatively low. US is primarily still a coal state, but we're moving away from that and so forth. Where I come from, we have, this was last year's source of electricity for the area of Illinois where I live. 66% was coal, nuclear was 14%, wind was only about 7%, but natural gas only 11%. So you can see it's not as clean an energy because of that. So I'll skip the next slide. We're continuing work on this. We're doing work in terms of how to select the vehicles for the various services, and also in terms of the implementation of this communications infrastructure, plus an effective incentive program. So I'll conclude by saying that I presented the framework here in terms of integrating battery vehicles into grid, both as loads and as resources. They can be very beneficial. Only thing that we need now is for somebody to go out and tell the people, please buy that car. And we're going to start seeing those kind of advertisements coming in, because this is going to be an important market. And so vehicle to grid, we're starting on something which can be very big, but we need the people to buy the cars. So I'm ready for questions.
The floor is open.
Yeah, how do your models and processes work between urban and rural environments?
So we didn't go to that finer grid in terms of resolution. I'm sure we could model it, but if one of the issues is going to be the distance, and so if you're talking about relatively remote rural environments, then that's going to add to the distance, but that's going to mean a cleaner environment. The issue is, what is the electricity which is being charged into those vehicles? So it will depend, but we could do those kind of studies. It's a good question. It's important to start looking at this. Most of my colleagues have been working on all the issues in terms of how to schedule the charging, the discharging of those vehicles. And that to me is a secondary effect, because we need to have these vehicles being bought, and it's moving very slowly. Less than 0.5% of the vehicles in the United States today are electric vehicles which are being bought. So there's not this rush over here, but it can be like a pet rock. Somebody has to plant some ideas, and then people will start buying it.
Any other questions? I have a couple of questions, George.
Oh, it's only one question per customer, but for your case, we'll make an exception.
I'll make it one then.
Okay. No, it's okay.
One of my questions is, you present a business model in which basically the aggregator buys these batteries and then sort of rent them to the
Right.
vehicles and then use them as he wishes. This business model, with all the issues of B2G, the reluctance of customers to, I guess you didn't discuss incentives, but I guess depending on incentives, whether they are willing to provide the service, participate, etc. That business model versus a business model where this same aggregator or same company goes and buys these second purpose batteries and then generates these stationary services to provide similar services. How would you?
Yeah. So I mean,
the issues?
so that's a totally different. That's more the model that I think Elon Musk wants to use, because he wants to go and compete with the distribution companies, where he's going to sell people storage devices. So mine is still a concept. I mean, nobody has used it and said that they went to the bank to get the loan for that. But I think there's something either that the utilities can take on, because the utilities keep talking about these death spirals. They keep talking about other guys want to eat our lunch. This is here a model which they could use, and they could implement exactly the way they wish. They have good credit lines available. They could be in this business. But this is not what they think that they should do, and so they let other people eat their lunch, essentially, if they don't follow that stuff. So I'm not saying that we can't do all kinds of modifications in my plan, but I'm looking at the aggregator, because without the aggregator, this V2G doesn't go. Okay, I can't have people act in a disciplined way without having a leader there who's going to send them the appropriate signals and do the charging, discharging, and so forth in an organized way. So I'm open to other suggestions, but this is as a starting salvo in terms of trying to get people to opine on this and to see how we can tweak it to make it more effective. But I think it's an important one, because utilities are very excited about the V2G idea. They're excited because it represents new load. In the United States, most of the utilities have lower demand today than they had in 2008, before the financial crisis started. Okay, so the demand has just not grown at all over the last 7 years. And only now it's starting to pick up. So you have proposals from San Diego Gas and Electric. They want to increase rates by $100 million, which they would spend to put in something like 500,000 chargers throughout their system. And they don't run such a large system, because it's essentially metropolitan San Diego. But they see it as the best source of new load that they could attack. And so they're trying to get the rate structure in such a way that they put in these services. We've done some work on a totally different subject like this. We wanted to see how you would collect taxes on these vehicles, electric vehicles, so that it doesn't in any way come in and reveals where you went and so forth. But if you go through a certain jurisdiction which has to have road taxes, they would collect it. Okay, so this was something else. So it sets up a whole bunch of new problems. But mine is a start.
Sorry, my second question, in spite that I only had one.
That's okay. You're a very good friend, Claudio.
So I'll get that preference. My second question was regarding the incentives. You did mention incentives sort of briefly. Have you looked at the kind of level that motivate people to get engaged into something like this?
No, that's why that part of the work, I'm trying to get a collaborator in the business school. Okay. I mean, I can be in many different fields, but I don't want to threaten them that somebody from engineering is taking away their bread.
Okay. Any other questions from the audience? Yes.
So with the system, new cars, like new electric vehicles, would you ideally like to see, like, say there's an aggregator that exists, would you like it to almost be an opt-out so that if someone buys an electric car, it automatically does this unless you look it up and, you know, say I don't want this? Do you want it to sort of be just like an automatic feature that every car comes with this, and then if you bother to understand it and research it?
How would you answer that question? I haven't thought about that. It's not that I'm trying to deflect, but I would think that those guys would want every mailing list where they can send, instead of 100,000 emails, 1 million emails to get everybody who buys a car. So they probably are going to go in and try to either mine it from there or from the registration. You know, for example, in Oregon, they charge you a higher registration fee for an electric vehicle because this guy doesn't have to pay gasoline taxes. So they do it that way. So because it's collected by the government, it has to be public information. I mean, I talked about V2G, but one of the privacy issues is that, say, the guy doesn't come home to charge his car, but he stays at his girlfriend's house, and then his wife gets a bill for discharging over here. Okay, so that's not a very good thing. So those kind of things have to go through the aggregator, so they're evened out. So the aggregator can provide some defense over there.
You spoke about Apple earlier, and design seems like the ultimate solution to shifting human behavior to a point where consumers are just ready to adopt. Who do you see as the ultimate design partner in this?
No, I mean, I'm very serious about, did you see the number of people who wanted to buy the iWatch? And they won't get it for another 6 months, okay? It's like you're paying up now so you can be eligible for that. There is an amazing power of attraction. I mean, I had a Mac since I came to the university because my presentations were in that form. I went to Italy in 1999, 2000. I was the only guy in power engineering who had a Mac. They didn't know how to connect it. I couldn't give any presentations. I always had to put my stuff on some other people's stuff. So now Apple is doing so well. They're very interested in cars. They're trying to hire every power electronics guys who graduates in the United States because they want to build a whole thing with cars. So the mobility issue is very big. And they're in the midst of innovation center over there. You know, we make fun of California because we always say California has to implement it first. They make the mistakes, then we learn from it, and then we do it the right way. So Apple is going to be an important player. And they have deep money. They have so much money, okay? I use that as a kind of a funny statement on Jobs because everything he touched turned into gold. I mean, nobody else has done that with a product. I mean, I did not meet anybody in China who did not have an iPhone, okay? And it costs a lot more over there than here in North America because of the pricing that we adopt. So they're amazing marketers. And that's what we need. This is a marketing issue. But nobody is going to go out and buy an electric vehicle because they want to be the good guy for the utility company. I can assure you of that. They don't love the utility company that much.
Isn't that what Tesla is doing, basically? Selling these?
Tesla at one point, before Elon Musk came in, a Tesla used to drive in, they would remove your battery and replace it with another battery, and then you drive out. Always in a minute, okay? So it was very easy refueling stuff. But now they have stations all over the United States. Tesla, by the way, is the only company that sells direct to the public. So in certain states, they cannot sell the car because the state legislature had enough lobbyists from the car industry that you have to sell cars through dealers. So there are states where they can't, but they can sell it in California, where Tesla got there before. So, but Tesla is really amazing. They do have now a network, and they took this drive from the West Coast, just south of LA, all the way to Manhattan, and they did in something like 58 hours with refueling stops along the way. Combined, there were 2 guys doing it. And so they did 58 hours for that. So that's pretty good. I did it in 1971 when I was at Berkeley. From Berkeley all the way to Montreal, it took me 55 hours, but we had 6 guys driving. So that's the way we did it.
Very well. Yeah.
So I just have a question regarding the state of the charge of the cars that are operating under the aggregator will certainly have an impact on the performance of the aggregator to provide the regulatory service.
Sure.
So my question is that have you looked into how would that state of charge be after they are participating in all these services? It might be that it's not a normal distribution anymore because you are encouraging those with less state of charge to be charge more and those with higher state of charge to discharge more. So it might go more toward a flat distribution.
So those are open questions, and that's another reason to try to put the aggregator into that business, because this could be essentially an issue of how well does he know how to manage those batteries? How well does he know? Should he do that Robin Ness fashion every 6 seconds or 12 seconds? Is that better for the battery and so forth? That information may exist at the level of the battery manufacturers, but it's not available in terms of the literature. We looked, and we also developed like a state of health metric and so forth, but only as the battery manufacturers know that stuff, and they're not making it public. I mean, it must be proprietary information. All I can tell you is that the United States government, as part of the simulation package, it gave money to a bunch of battery companies, storage companies. They must pick them very well because each of them has gone bankrupt since, okay, with a stimulus package money. A123 was one of the guys with the lithium ion. It's a Chinese company today. Which one?
They've renamed themselves B456.
Okay, I think B456 has a good name. It's kind of a luck name in China. There's a restaurant, 456, Shanghainese restaurant in Chinatown in New York, so I know the name 456.
Any further questions? If not, I would like to take Professor Thank you.
Thank you.